The scientific revolution starts now.
Demystified broadcast.
Let us see in the dark.
I saw a tweet the other week that can be sort of interpreted in PG-13 or R-rated ways. That was like, you should do as your career what you did best when you were age 13 to 18. So when I was a teenager, as far as the activities I did that were closest to something professional. So I really enjoyed playing with my chemistry kit. And back in those days, like they didn't have the lame chemistry kits they had now. They had like, actual chemicals that you could mix together in ways that the kit did not suggest and, make new things. So I really loved playing with that. And I loved rocks as well. So I was like obsessed with geodes and trying to find them. I didn't like have a strategy or anything like that. I just go out and like find some round looking rocks and try to break them up. So yeah, I was into chemistry. I was into rocks. And although the field that I'm in now, it's not technically chemistry, it's not technically geology, but what I do is I study magical, not exactly magical, but seemingly magical rocks that are engineered with chemistry to have different properties and do all kinds of different things.
It's interesting because I feel like chemistry is a really physical discipline, because more than physicists, I feel like chemists have to have an understanding of the way that the molecules are relating to each other, because it's a shape-based science. And so I wonder if you come at it more from the mathematical side of things, or if you come at it more from this is what this molecule probably looks like, and this is how its appearance informs its characteristics.
So I would say that my approach is maybe more condensed matter physics than either chemistry or math. So both are kind of tools that are used in my research, but my training is really not in either of those. So maybe I should clarify when I say like new materials and novel materials, quantum materials, what I mean by material, because it does mean something a little bit specific in my field. So the types of materials that we study, and a lot of materials physicists study, they are something called crystalline solids. So in sort of common parlance, the word crystal, it can mean something transparent, something sparkly. But in physics, crystal means something very specific. It means that you have a regular arrangement of atoms that goes on and on for many repetitions. So millions and billions of encountering the same group of atoms over and over makes a crystal. And you can make crystals of all different groups of atoms, but generally in my field, we're making crystals out of like small groups of atoms, not something as big as like a protein.
And so when you're, because I mean, I had a hard time with physics when I studied it, because at some point it became really mathematical. Mm-hmm. Like there was a point with Newtonian physics and lenses that you can, at least there's a clear diagram that you can draw out, and you can think about bodies that are interacting to produce something. But when I think about condensed matter physics, I imagine that it's a very mathematical discipline with not a ton of visual representations. Is that the case?
So not I mean, there's always math, not only in physics, but in every science. But there still is maintained kind of visual representations, and also sometimes verbal representations as well. So a lot of things can be visualized. I guess, what can I add to that?
Because I think about
yeah, go ahead.
I think about something. Oh, go ahead.
I think what Anastasia is talking about is not totally visualizable in a schematic sense, but structural elements, right? So chemists are often like lock and keying chemicals together and looking at the ways that the different orbitals attack one another and so forth. And I think that maybe that's more the crux, is the structural elements that contribute to conductivity.
Yeah, because I think about biology, right? So my background is biology, and I think about genetics, which is probably the most abstract of biology, right? Because you're not dealing with an organism that you can look at behaving. You're looking at something that you usually get data for only after you send something to get sequenced, and you get a bunch of numbers, and you're reconstructing things off of pixels. And it is a discipline that benefits immensely from all of these visual tools. Like, so if I get a sequencing reaction back, it's literally like a picture. I don't know if you've ever seen one of these before, where it's these little curved traces, and they show you at each position which is the LED that lights up, and it shows when there's multiple together that there's different ratios of them. And so as you're working with it, you have a really visual picture of the thing that you're working with. Or if I'm cloning in the lab and I have a plasmid that I'm making, I have a plasmid map. And everything is marked out on the plasmid map of like, this is where this sequence is, and this is how it fits together. And there's this puzzle of having to actually think about the sequence and how you have to make like the reciprocal version of the sequence in order to bind it together. And so for me, biology is really a discipline that's very physical. But structural. But then I look at physics and I'm like, I think that physics isn't like that. I feel like physics is really... the intuition that you have to develop is a mathematical one rather than a visual one.
Or schematic,
yeah.
Yeah, I mean, it's all of the above. And I think there is an intuition that needs to be developed, and that intuition is different in different fields. So when you describe these kind of visual things in biology, they're a little bit foreign to me. But separately in physics, there are other visualizations that we have that are, it also is intuitive once you've been trained, but it's a separate path of training than biology. There is math that goes into it, but there's, that math throughout the whole way is accompanied by graphs, visualizations. It's accompanied often by sort of demos, either in the lab or like on the computer. So there's definitely a training to get the intuition, and there is a visual component as well. I mean, the experiments that I do in my lab, there are pictures that come out, and many concepts in physics, I think of them visually.
Yeah, because like when we think about conduction bands or something like that, it's very much like a schematic. It's almost like a tabulated way of looking at these changes, right? Because the changes in conduction are energy state changes, which is already pretty abstract. It's not some simple like leg bones connected to the hip bone kind of situation. And I think that scares a lot of people off in some sense. But I don't know. What do you
Is it a problem to be solved?
Yeah.
Maybe. I mean, it could be a communication barrier, but I don't know if this is a simpler concept, but when you have an atom, it has sort of discrete energy levels, and then there are transitions that can be made from those discrete energy levels. So if you have many atoms together, instead of having like energy levels far apart, you sort of have bands of energy levels. You have groups of energy levels that are so close together that it sort of behaves effectively like a continuum. And then there's a gap, similar to how in an atom there's gaps between the discrete energy levels. So there's visualizations you can find online of like, okay, this is the energy levels of one atom. Then you put two atoms together, like two hydrogen atoms, for example, and you have like double the energy levels, and then you keep adding more, and eventually it coalesces into bands separated by band gaps.
Yeah, and those energy levels sometimes correspond to shape changes in the surface of the atom, right? You get these different orbital shapes in different energy levels sometimes, but not always. Certainly, like it seems like in metals, the conduction happens in just this. Maybe you can illuminate that a little bit. It doesn't have so much to do with these shape changes so much.
Yeah. So good. We think about things, I would say, in both ways. So we do talk about orbitals and how the orbitals of individual atoms interact and overlap with each other, and how that connects with conduction. So that picture is sort of like a real space description, and it's the default for most people, and I'll explain in a minute why we don't always use it in condensed matter physics.
The Demystify Sci podcast is an independent media project that is supported by viewers like you. In order to keep the lights on, the guests coming, and the production levels high, we need your help. Come over to patreon.com/demystifysci and contribute a couple dollars a month to help us keep the ship going. In return, you get all of your episodes early on Saturdays for the week. You also get to join our very, very, very good Sunday patron conversation, where we get together and we talk about the ideas that have been brought up in the episodes that week in places where people have been reading. We make plans for what the future of the show is going to look like, and it's something that you can participate in even if you don't want to turn your webcam on. There's an active chat, and so you can just come and watch, or you can come and participate. If you don't have any spare cash right now, that's totally fine. You can tell your friends about the podcast. You can come to our Discord server. You can leave a comment on YouTube, and all of these things help boost us in the world so that more and more people can find us. And finally, we have one more thing on the books that we are incredibly excited about, which is our upcoming conference. April 6th and 7th of next year, we plan to meet in Austin, Texas. More details on that are coming, but for right now, consider just blocking off those dates in your calendar so that we can meet up next year. For right now, back to the conversation about quantum.
But anyway, when you think about orbitals, that's kind of a real space picture. You can think of the orbitals hybridizing with each other, sharing electrons, or you can think of electrons hopping from one orbital to another. And sometimes we use that language and we use that visualization. Another way to think about often the same situation is what in physics, in condensed matter physics specifically, we call momentum space. So this is kind of where there's the dividing line between, like, I guess, normal person intuition and like physicist intuition really comes into play. And this is something that a lot of students struggle with. But once you get over the barrier, like, you start thinking in this new space called momentum space. So the rationale for momentum space, so it can be seen in a couple of ways, but I like to basically start off with the idea that electrons can behave like waves instead of particles. So oftentimes in metal specifically, it's easiest to think of electrons behaving like waves. And another way to say this is that they are delocalized over the entire metal. So when something is delocalized, it doesn't really make sense to talk about its position. But for a wave, it can make sense to talk about its wavelength. So it turns out that an electron's momentum is related to its wavelength. So we sort of group things by group electrons by their wavelength rather than by their position. And we use this to visualize sort of the delocalization of electrons in a metal and some of the implications of that. But ultimately, the picture of like orbitals in real space and these delocalized electrons in momentum space, they are more or less equivalent. They're kind of describing the same elephant in two different ways.
Yeah, it's almost like the momentum space is the dynamic component of it. Like, I think, I know there's some failings with this analogy, but the Newton's cradle analogy for how this momentum is transferred. Like the electrons themselves don't have to wander through the entire wire in order for them to instantiate some motive force at the other end, because they're in contact with one another. These atoms are all in contact, and in essence, they share some surface, it seems like, or they share this outer electron in a diffuse way.
And it totally makes sense, because I was sitting here and I was thinking, I was like, why would momentum and wavelength be related? Like on an intuitive level. And the Newton's cradle thing makes sense because wavelength would be the frequency with which that pulse passes through the cradle. And so the shorter your wavelength, the more of those pulses pass through in a given moment of time. And all of a sudden you have a very intuitive relationship between wavelength and momentum. Because we're not actually getting a flow of electrons in a metal.
It's very slow.
So let me just clarify something there. So in the context that I'm talking about, momentum is kind of a descriptive attribute of electrons. It does not, however, imply that the electrons are doing mass transport anywhere. So at this point, like, I'm just talking about a chunk of metal or a chunk of anything, really. And we are not like sticking it onto a battery. We're not applying an electric field. And if you don't apply an electric field, the electrons as a unit are not going to transport anywhere. Each electron will have an attribute of some momentum, but these momentum vectors will all cancel out because they're pointing in opposite directions. So,
like in random directions, right?
Random directions, exactly.
And so it seems like what happens.
Well, not exactly random, I should say. Like there is some, there might be some, I guess, directionality, and there typically will be in a real crystal. So it's not fully random, but it averages to zero. So if you have one momentum vector that's pointing in this direction, there will be an exact opposite in the other to cancel it out.
Interesting.
And these are just intrinsic properties of the lattice itself.
So it's it's a property of electrons interacting with the lattice.
Gotcha.
The lattice is the periodic array of atoms in this crystalline solid.
But then when you hook it up to a power source, all of a sudden you have something that is a directional force that is...
That's right. So yeah, each electron starts off with some momentum, and those momenta together average to zero. And then when you apply an electric field, then it gives kind of a little kick in the same direction to all of them. So it adds another momentum, or one can think of it as like giving a little momentum boost in one direction. So the average is no longer zero, but it's something. And then you have mass motion. And this is a huge simplification of how conduction works, but it's the general. It's like what I present in an undergrad solid state physics class.
What do you think are the details that get lost in the simplification?
So it's a necessity to lose some details. So you start off with the simplest possible explanation, which is the one that we're talking about now. So initially, electrons, they all have momentum, but it averages to zero. You attach it to a battery, and this imparts a net momentum to all the electrons, such that their total is no longer zero. So that's the simplest explanation. There's a lot of different things that are lost there, stemming from the quantum mechanical nature of electrons. But it's actually pretty complex to accurately calculate the flow of electrons, especially when you're dealing with kind of incomplete information, or you're dealing with a simplification of your material as like a perfect crystal of, very regular atoms.
Is there any chance that you caught this YouTuber Veritasium series on the flow of electrons and the instantaneous exchange at a distance and all of this? So there's
No.
quite some hubbub on the internet.
He did a video about pointing vectors, basically, where I think that the title of the video was Electricity Doesn't Flow in Wires. And he did all of these simulations to show that if you have a circuit, it doesn't matter how big the circuit is, the minute that you close the switch, you begin to see a current on the opposite side of the circuit. Right? So if you imagine a rectangular circuit, and he made this whole thing where he was like, okay, so imagine that the circuit is 1 light year across. How soon will you see a current in the wire that is directly across the battery as soon as you close the switch? And it turns out that it's much faster than the amount of time that it takes the current to travel a circuit that is 1 light year across.
Yeah.
It's actually related to the distance of the wire from the power source.
Okay. Yeah. I mean, there's very different timescales involved of different components. So like, if you can find a way to track a single electron, then it will, when you have the power supply connected, it'll traverse very, very, very slowly. On the other hand, the time to get for every electron to get information about, okay, how big is this electric field? How much force am I feeling? That is much faster. That travels at the speed of light.
And what was interesting is that it didn't appear to travel through the wires. It appeared to travel across the circuit to the other wire, which I think is kind of inherently, it makes sense because we know that, I mean, it made sense to me because I was thinking about the way that a current inside of a wire creates a magnetic field. And so if you have a current that suddenly begins after you close the switch, it makes sense that it would induce some kind of change in the wire that's directly across the circuit. But there was a big hubbub because I think that it was the first time that a lot of people had started to look at the idea that the model that they're presented in undergrad, which is that, okay, you have because you see these pictures, right? These little balls of electrons flow through circuits. And I think that it's kind of a heartbreaking moment for people to realize that that picture of how electricity works, a thing that they've been convinced their entire lives that they fully understand, when they realize that that's not actually how it works.
Yeah, I mean, I can sort of see that. On the other hand, like in physics, in explaining physics, there's a lot of simplifications that just work. And I guess people have different opinions of this, but I'm kind of the opinion, if it works, then it's good enough. Let me give an example of this in my teaching. So like when I teach freshmen and sophomores, when I teach like the introductory, like baby quantum mechanics course, there's something called the Bohr model of the hydrogen atom, which was a model presented by Niels Bohr that sort of predated the full development of like describing an atom with quantum mechanics. So the Bohr model is kind of a quasi quantum mechanical model where it basically assumes like a planetary model of an atom where you have like your nucleus and then an electron orbiting around. So the little component that is kind of quasi quantum mechanical is that the electron, its orbit, it has a certain radius, and then the electron is described by a wavelength such that you can fit like an integer number of wavelengths in that orbit. So that's kind of the quasi quantum mechanical description. So the Bohr model is wrong. Like it's not the proper way to think about an atom.
But it looks so cool.
I know, but at the same time, it gives the correct answer as far as like the energy levels of hydrogen. It gives the correct answer, and not only does it give the correct answer to that, it also gives the correct answer to other effects. Like for example, if you have a nucleus in hydrogen, normally it is just a proton, but you can also have a proton with a neutron. It's called deuterium. And this isotope effect, the wrong Bohr model gives the correct answer to that as well. So this is an example of a model that is wrong. It gives the correct result for experiments that you can show to undergrad physics students. And for that reason, a lot of people still keep it in the curriculum, and I like to keep it in the curriculum, sort of just to build some understanding or some memory of a specific experimental result, which then we can return to with more rigorous formalism. So I think these wrong descriptions can sometimes be useful if it sort of builds intuition or recollection about real results, real experimental phenomena. And then at some point, a wrong simple model can break down, just like more sophisticated models can be proven incorrect with new experiments.
Yeah, and going back to what we were talking about earlier, it seems like a very structural model, right? It's easy for people to represent it, and I don't know, you have the quantum jumping there that starts to have a visual component to it and shows these little breathing atoms, which is really nice. But yeah, I think there is something interesting there where all models, in some sense, are limited. And,
Right.
I think this is Gödel's incompleteness theorem, which is just no matter what you do, there's always going to be new things that emerge that your model can't possibly account for. And so it seems like something really healthy about having a plurality of models when it comes to scientifically describing nature in order to, whether it's to make a technology or to just get at what's happening. It's very difficult to have a single model.
Yeah, absolutely. I think it's when you present models that are known to be incorrect, I don't really view it as a lie. I view it as like a simplified explanation for an audience that needs to start off with a simplified explanation. So a lot of like popular science communication is via analogies, and analogies are ultimately wrong. But in a classroom context, you need to do something similar as well.
Well, it's interesting too that when we were talking earlier about, how structural and visual something like condensed matter physics is, there's, like you said, a visualization that comes out of it that's often in the form of graphs or data or something that's visual that is reflective of what is being measured. But I wonder if at the highest echelons of physics, people have a better visual model that they carry around inside of their heads than the Bohr model.
Oh yeah, absolutely. So for an atom, yeah, absolutely. So in that same baby quantum mechanics course, right after we learn the Bohr model, we kind of throw it away and start over from a more quantum mechanical model, which gives us this concept of electron clouds in an atom, and sort of the different orbitals and their different shapes. And this electron cloud, it represents something physical. It represents kind of the probability of finding an electron in different locations. So the cloud gets kind of more diffuse as you go further out, which is a physical thing. So this more realistic model, it's mathematically a little bit more challenging. But at the same time, it can still be visualized. So at the end of the day, you get a what we call a wave function, which can be related to a probability of finding an electron, and then you can just either you can write a simple computer program to pick random points in space and assign it and then assign it a value based on what the probability of finding electron there is, and then in short order graph out this electron cloud.
What's really fascinating to me about that is, you do like the radial distribution transformation or something, and you eventually get where you get this picture of where the most probable location of this electron is, and it now functions, when we move into the material level, it functions as a surface all of a sudden. That's really fascinating to me. Like it actually it seems to, if we're visualizing the orbital structure or something, it seems like that probable location starts to become where the material is at, almost.
Yeah, I see what you're saying. So yeah, another visual model that we use when describing these crystalline solids, these materials, is sort of these ball and stick models, where we have like a bunch of balls connected by sticks, making like a regularly repeating structure. And this is a common visualization tool. Many older professors have them in their offices. Back from when you didn't have the luxury of digital tools to explain the same concept.
Or even if you even if you do like an AFM scan, right, of a surface, you kind of see this, right? It seems like it really is a surface that appears at that, where the 99.9% of probability of the electron shell is located at. It's like,
yeah, I would say yes and no. So like in our macroscopic world, we kind of, the surfaces we deal with are kind of more absolute. So like the surface of the table in front of you, it's kind of a very rigidly defined surface. I don't know if you can smash your hand through it, but it won't be easy. So that's kind of our intuition of surfaces. But in the world of atoms, it's not quite so such a hard cutoff. So for example, in materials, they're not literally hard shell spheres. So if you have a certain material, you can mush the atoms closer together. It's not easy, but you can stick the material between two diamonds and you can make that happen. And also when you raise the temperature, usually materials expand. So then the effective size of your balls appears larger, but this just kind of reflects the fuzziness of this electron cloud.
But it does seem to act sort of like a pressure boundary in that sense. Like when you squeeze them, you have to displace all of, I don't know, it's like almost like you have to displace that surface. Maybe, with turboelectricity or something, you're actually spooling up the electron somehow in doing that. It's like, it's interesting how they do form some sort of effective surface in the context of various physical interactions.
Or at the very least, it seems like it could be modeled as one.
Yeah. So, I guess there is sort of an effective size of the atoms. And I would say a more realistic model than just like hard balls bumping against each other is you can have hard balls, but then springs between them. So sometimes the models in the old professors' offices, they will have the balls on springs. And that, I think, is the more accurate visualization. So you can sort of push them together and pull them apart a little bit. And that is actually pretty accurate. And like in a material, the atoms, they're not literally on springs, but this kind of gets to a really cool thing about physics, or a not cool thing if you don't get concepts the first time around. But in physics, like we kind of learn the same thing over and over and teach the same thing over and over in every class and every subfield. And one of these themes that we come to again and again is something that in physics we call a harmonic oscillator. If it's quantum mechanical, it's a quantum harmonic oscillator, but it's just a spring. And the reason that this shows up over and over and over is because typically systems, and I don't just mean materials, I mean like almost anything, it's going to be in some energy minimum. And usually it's possible for it to move away from its energy minimum somehow, raise its energy a little bit, and do it along different coordinates. So the potential energy landscape that it lives in is similar to that of a spring. So going back to the model of a material as these balls on springs, so that is a pretty good model, at least of the atoms, because each atom, it sort of sits in an energy landscape that looks like that of a spring. So mathematically, it's very similar to a spring. There aren't literally springs, but for all effects and purposes, you can really quite accurately visualize it that way.
I think that a mathematical Zen koan would be like, if it acts like a spring and it looks like a spring, can you call it a spring? But I totally understand what you mean. Like, there's not actually like the spring structure down there, but what does it mean?
Well, it's like, I mean, all of my PhD was in elastic mechanics, and I worked a lot with the AFMs and so forth. And it just, the more I started studying quantum mechanics, the more I had a hard time not seeing atoms as fundamentally elastic structure, like elastic materials of some sort. The equations are so similar to various elastic mechanics, especially when you get into the torsional aspects of the AFM and so forth. You just start seeing these similarities in the behaviors. And so I think that it's, it is a great analogy, but I think there's something there too. Like, I think there is something elastic about the atom, which is interesting.
Yeah, absolutely. So I guess, there's like verbal analogies that people sometimes use that are almost by definition incomplete. However, when the analogy is not verbal but mathematical, I think that is where you can sort of exploit universalities of nature. So you get very similar looking equations in a lot of different contexts, and in that case, if you can solve the equation, you can solve the equation, and you can take it as far as it goes. So one example of like math that shows up everywhere is things that look like springs. So that kind of math shows up everywhere, with pendulums, with actual springs, with atoms in a solid, and so on and so forth. Many examples. Another type of equation that shows up in a lot of places is waves. So like you have wave-like particles in quantum mechanics. Maybe that's not the best place to start. You have like pressure waves in air, also known as sound. You have waves in water, obviously, and you can use the same equations. Plucking a guitar string, so you can use the same equations for all of those, and at some point you do need to consider the specifics of the different types of waves, but you can take this mathematical analogy as far as you can. It's not really an analogy, it's sort of a common description of different phenomena.
Yeah, the transport phenomena are another good example of that too, like heat flow and momentum and things like that, diffusion. It's striking how similarly nature quantitatively reiterates itself over and over and over again.
Yeah.
Well, that's one of those things that leads people to think that we live in a math-first universe, right? That's kind of a philosophical thing that hangs around at the bottom of physics that I think is really fascinating, where I think that there's some people that genuinely believe that we live in a mathematical universe in the Tegmarkian sense, which is that all there is down there really is just equations. And then there's other people who I think are probably more philosophers than physicists that would probably be binned as materialists. So people who say, look, if there's math that is at the bottom of things, that math is describing a thing. And so physics is done on the back of this metaphysical split where physicists have kind of generally accepted that what's down there is math. But that's not an intuitive thing to accept as a person who lives in the world.
Yeah. I mean, mathematical, it's interesting. Mathematical intuition math is hard for a lot of people, partly because it's not taught very well, or it's expected to be hard. So math is hard for often. So it's not natural to think of sort of the observable world around us as being mathematical. Ultimately, I think a lot of it is, if you want to describe it, but it's not. I mean, it's one tool of of many. I think math could describe everything, but sometimes it's the more complex description as opposed to going another route. So in physics, we like an alternate thing rather than kind of back of the envelope math, or not back of the envelope, but pencil and paper math is simulation. So doing sort of computer experiments, which for you still have to make simplifications and models there, but it's kind of a related but almost alternate route. And in other fields of science, there's probably other descriptions that are maybe more useful.
Well, I mean this like in a deeply metaphysical sense, though, right? Because I think that if you go to so correct me if I'm wrong, and I could be totally wrong, but I've gone to the bottom of quantum field theory, and at the bottom of quantum field theory is a field which is changing, which is vectors that change over time. And that to me feels like a mathematical object. And so quantum field theory would suggest that at the bottom of reality is a mathematical object, which is a conceptual object, not a physical object. And so it seems like the idea that there is a physical material body down at the bottom that the quantum field is measuring is a philosophy that went out of fashion probably, I don't know, maybe even 100 years ago. Right? It was like the death of the ether and Michelson-Morley and the appearance of general relativity and special relativity.
Quantum physics, really.
Quantum physics, yeah, right? Because you have all the spooky stuff that happens. And so because you cannot conceivably imagine an object, a body, that follows all the rules that you've discovered through your experiments, the discipline kind of leaves behind the idea that there's a material foundation at the bottom of all the math. And so when I encounter it now as an outsider, right, no alternative claims, definitely an outsider. But I walk into it and it feels like a place where I go to seek answers, because my biology was in bioelectricity. And so when I was doing my PhD, I was studying charge inside of cells. And I couldn't get to the bottom of what was charge. Like, I'm studying a physical discipline. There's like atoms that are bumping up against each other, and I try to figure out what charge is, and the explanation for charge is math. And I'm like, well, hold on a second. Like, surely we have to have a model for what the atoms are doing that gives them charge. How can I think about this otherwise? But I feel like physicists are generally comfortable with, we have the equations work, and the question of what is charge is a very difficult one, and we don't have that.
I mean, there's many different types of physicists. Physicists, their research extends throughout the entire observable world, very small things, very big things, natural things, man-made things. So I would say the answer would be very different depending on what kind of physicist you're talking to. So there's like a level of abstraction, I guess, that sometimes you need to accept to move forward in your subfield. So, like, for example, for the type of work that I do, it is sufficient for me to sort of stop the abstraction at the point. For example, an electron is a particle that has certain attributes. It has certain rules, and those rules are it has a certain charge. It has a property called spin, which is sort of like a little magnetic moment, but not exactly. And it has when this spin is considered quantum mechanically, it also follows certain rules because it is a spin 1/2 fermion, meaning that it cannot be in the exact same quantum state as another electron. So that's just an example of a specific area of research where you can just stop the math, stop the abstraction at a certain level, usually. And that level might be very different for other fields.
Is there a field, though, that goes beyond that level of abstraction?
Definitely.
Okay.
Yeah.
Yeah, how do you think about these problems? Like, I want to talk a little bit about the problems that you're working on in your lab right now. And, Yeah, like, do you think in terms of the math primarily? Do you think in terms of the lattice arrangements? How do you think about these materials?
Um, so I don't think about the math too much. So I see math as kind of one tool that is used, and it might be underlying some things that are kind of more intuitive to me now, but it's very rare that I'm like doing pencil and paper type of math outside of like teaching in a classroom. Um, so um, the uh, so I visualize. Maybe it does it help to back up and talk about the experiments
Yeah,
that
yeah, yeah,
that I
sure.
do? Okay.
Let's do that. And then we
Uh,
can get back to how you conceive of them.
yeah. All right. So, like I said at the beginning, my group studies how electrons move, and we study how they move in crystalline solids. So, this is an important thing because almost every useful property of materials, particularly sort of in terms of ultimate technological applications, is because of their electrons. So, like the copper wire in my house, I hope it's copper, is has the charge carrying characteristics it has because of how electrons behave there. The windows, the electrons there behave in an insulating manner, and that also determines their useful property and being transparent. The semiconductors in the devices that we're having this conversation over, there's other attributes of the electrons that need to be sort of understood and engineered in order to produce the characteristic behavior, which is ultimately little tiny on-off switches called transistors. So electrons ultimately are everything. Um, so um, we talked about this concept of momentum space for describing electrons. That's kind of a very useful organizing principle for talking about many quantum particles, where at least at the starting point of the model, they are delocalized. So it's not really useful always to think about their position, but rather a momentum. So what we do is we study how electrons move in momentum space. So the way that we study it is actually dating back to Einstein. So we use the photoelectric effect. So the photoelectric effect is where you shine light on, when they describe it, they say it's a metal. It doesn't have to be a metal, but you shine light on a metal and then electrons fly off. And usually when people are taught the photoelectric effect in a classroom or in some popular science setting, that's just where it stops. So light in, electrons out, that's it. But it turns out that those electrons are still carrying information after they are kicked out of the solid. They're still carrying information about how they were moving inside the solid. So basically by using energy conservation and a type of momentum conservation, we can get the energy versus momentum that electrons had back when they were inside the solid. And energy versus momentum is something that is called a dispersion relation, and it tells us very detailed information about how electrons move in a solid, and relatedly how they would respond maybe if you applied a voltage or various other real world situations. But the dispersion relations, energy versus momentum, is kind of the starting point for everything. And even classical objects observe dispersion relations. So like if you throw a baseball it has a certain, you can describe its momentum. Now I'm talking about classical momentum, mass times velocity vector. And you can connect this momentum to energy. So if momentum is given the letter P, then energy for this baseball, kinetic energy, is equal to P squared over 2m. So the energy goes quadratically with momentum for classical objects. So for electrons,
And the m in this equation is the mass of the object?
the mass of the baseball.
Okay.
Yeah. So classical objects pretty much obey one dispersion relation. And when we're talking about electrons in a crystalline solid, in the simplest case, they also behave very similar to the baseball. So they also have their kinetic energy going quadratically with their momentum. However, once you start getting sort of more complex behavior, then you start deviating from that simple picture. So you can have electrons in a solid where maybe the energy doesn't go quadratically with the momentum, but it goes linearly, so it behaves more like light. Or you can have the denominator change. So instead of so you still have some mass in the denominator, but that mass sometimes it is effectively not that of a free electron, but of something that is much heavier than a free electron. So there's many variations. So in a real material, the way that the electrons move is typically different from the baseball analogy, one way or another.
And is this because we're talking about groups all of a sudden? There's a lot of these electrons acting in concert together?
So
and you
yes,
end up with feedback and all sorts of complex,
so,
resonant interactions.
So yes and no. So you can in a crystalline solid you have all of the electrons, but you also have all of the atoms. So you can have interactions with the atoms, creating different behavior, or you can have interactions between electrons and all the other electrons, creating new behaviors. And I guess the more the case that is more poorly understood is the situation where you have all of the electrons interacting with one another, and you cannot somehow pretend this interaction does not exist.
All right. So what are the problems you guys are trying to solve?
Good. So when I was a postdoc, someone asked me, like, what is the biggest problem in condensed matter physics? And I could not answer the question, because in condensed matter physics, or even if we get like more specific, materials physics, solid state physics, kind of synonyms for the same thing, there are many interesting problems. So when you have the entire periodic table to play with, you can put the elements together in many different ways to get different types of crystals that have different types of behaviors. So I would say there's not one biggest problem in the field. There's many important problems. But if I were to kind of describe an overarching goal that we are not going to reach this century, if ever, but the overarching goal is to be able to have materials by design to the ultimate degree. So to be able to concoct like whatever recipe of behavior you want, and then with all of the knowledge of how materials behave, construct a material to manifest that behavior. So as an example, let's say you wanted to make a semiconductor to be used for solar photovoltaics. You want it to be made of earth-abundant materials, and you want it to have a melting point of, a certain value, not too low, not too high, so that the energy to manufacture it is not very large, but not so small that it just dissolves in the sunlight. So anyway, this is sort of a constrained design criteria that at this point, we don't completely have the tools to invent a new material based on that design criteria, but maybe in the future we'll be able to. And other types of design criteria are even more difficult. So we can come back to the topic of superconductivity, but like trying to design a room temperature superconductor based on certain design parameters, like you want it to be superconducting at a certain temperature, you want earth abundant elements, so on and so forth. That is another example of materials by design that we're even further off from than the semiconductor example. So,
Can I ask a really stupid question? I'm sorry. Sorry. Why are people so in love with superconductors? Like,
It's got super in the name. What do you mean?
You tell me. I don't know. I mean,
what is a superconductor?
I've succumbed to that as well. But it's a very interesting. I've been somewhat perplexed in a way, just because as far as materials physics is concerned, the only phenomena that really has any reach with the public is superconductivity, and usually room temperature superconductivity. So there were movies made about it, multiple ones. Yeah, I mean, it's I think part of it is that a superconductor has defining characteristics that are sort of straightforward. So it expels this magnetic field, and in the visualization, it levitates. And it also has zero resistance to current flow, which is another kind of relatively straightforward concept. So there's lots of interesting phenomena that materials undergo, but a lot of them have kind of more, I would say, more specialized descriptive characteristics. So like a resistance is something that you could, in principle, measure in your home, like with a voltmeter. I mean, I have one in my home. I don't know if that's a normal thing.
We've got two of them.
Okay, perfect. Well, yeah. So I think just
like, what is the
accessibility?
Yeah, what's the promise of superconductors? Like, what are some of the end game technological applications that people imagine?
I heard a lot of people talking about railguns.
Oh boy.
What's a railgun?
I think that it's a weapon that uses superconducting parts as the propulsion mechanism. Oh,
okay. So, okay. That's probably
so
a real application. Yeah, that's probably a real application. The Air Force at this point in time is probably one of the bigger funders of superconductivity research. Yeah, so I guess the applications, it depends on exactly what superconductor you have. And are we talking about room temperature ones specifically, or?
I'm just trying to wrap my head around why all of the hubbub about superconductors and why everybody's so excited about them. I mean, it might be just because super is in the name, like Nastia said, but I don't understand yet.
Well, I mean, okay, so if I think about something like maglev trains, I feel like right now the way that they work is using electromagnetic power as the driving force, right? You have a current, you have an electromagnet, the electromagnet causes levitation, then you can have a high-speed train because you have very low friction.
Right.
If you have a room temperature superconductor, the material itself can accomplish that without having to pump energy into the system. Like you construct
it's like a one-time payment or something. You charge it up and it's good to go.
Yeah, one-time payment.
And like when the LK99 stuff was happening, I think that it was really fascinating to people because it seemed like it was humanly possible to produce it very, very cheaply from these earth-abundant minerals, like you were saying, you know.
Yeah. I guess. So I would say applications is something that on a daily basis I think about and I don't think about, if that makes sense. So like
Very quantum answer.
Exactly. So as a physicist, as someone doing fundamental science, I'm sort of my job is to try to uncover kind of hopefully universal truths, but if they're not universal, at least they're true. And then what the market and what human ingenuity tries to do with that is someone else's challenge. So that's the sense that which I don't think about it. So, if I work on a material and then the market says, "Oh, it's too expensive to use it for anything," well, I mean, I'm not personally invested in like what I did experiments on in being applied. So that's the sense that I don't really think about it. But in the other sense, I think about it because in materials physics and condensed matter physics, we're kind of working with tangible things like real pieces of material, real crystals, something you can hold in your hand, put in the machine yourself. And this material, it does real things. Electrons do something in it. And the behavior of those electrons, one with very little creativity can imagine what it can be used for. So I think about applications and I don't think about applications. As far as room temperature superconductors, I think ultimately if we have a room temperature superconductor, the most useful applications will be something that we don't even conceive of right now. And then the things that we do conceive of right now, probably it will not pan out for various reasons. So kind of as an analogy of this, we can think about superconductors that have been known for over a century, which is like elements on the periodic table, some of them. And those superconductors, they were discovered in 1911 accidentally, as is the case with most superconductors that have been found to this day. So they were discovered accidentally. Mercury was the first one, but many other elements superconduct and intermetallic compounds as well. And in the early part of the 20th century, I don't know how the public perceived superconductivity, but I do know that it occupied some of the greatest minds of 20th century physics. So Einstein worked on superconductivity. He wasn't able to explain why mercury becomes superconducting at 4 Kelvin. Feynman did some work on it. Landau did some work on it. Every great physicist, I think, at that time did some work. And ultimately, what it took was sort of a couple of smoking gun experiments that pointed physics in the correct direction to explain why those materials became superconducting. So as far as understanding why those materials become superconducting, that was done in the 50s. And do you want to ask a follow-up, or should I keep going?
Yeah, keep going. Keep going.
Okay, good. So those low temperature superconductors, the science is pretty much settled on why they become superconducting. Now for the applications. So the applications of superconductors in our everyday life is pretty much MRI and only MRI. So I would say, so I can say with definitiveness that in 1911, when Kannerling-Onnes discovered superconductivity in mercury, he could not conceive of MRI because the physical principle of it, nuclear magnetic resonance, was still a discovery decades away at that point. But anyway, sort of the scientific impact of those low temperature superconductors was fairly large. The technological impact is relatively modest. So MRIs are an important imaging modality in medicine, but it's not the only imaging modality, and it has its advantages and disadvantages. And following up on that, so MRI, it's been, I don't know how long it's been around, but a while at this point. But in the 90s, these well understood superconductors kind of came back into the realm of what at that time was basic science. And in the 90s, people started thinking about, hey, maybe we can use these well understood superconductors for quantum information, for quantum computers. And that is a research that began in the 90s, and it hasn't exactly been commercialized at this point. I mean, it has, because the D wave and other things, but it's not like a general purpose technology at this point. But it's an example of kind of very settled basic science sort of getting incorporated into new basic science, which has sort of a goal, or a stated goal, I should say, of some technology, which is decades in the future. So these things kind of go in cycles. And again, I can say with definitiveness, whatever that word is, that the guy that discovered superconductivity in 1911 could not have conceived of it being used for quantum information a century later.
Yeah, it's interesting how each of the ages have been sort of led forward by these material advances, even if it's just like Stone Age to Bronze Age to Iron Age. And it's almost like people know that there's something else. There's another level of understanding we can get to. I'm actually like constantly blown away by, we interview a lot of archaeologists and anthropologists, and oftentimes these advancements just get tossed off in a single sentence. And I'm like, they developed metallurgy? Like, what are you talking about? Hold on. Like, let's talk about this. This is insane, because there are always these horribly technical issues in moving these arts forwards. And so I assume that's essentially where you're positioned, is that right at the cutting edge of the next material revolution. And so like, obviously efficiency is a goal. What are some of the goals when you're trying to develop materials that drive you forward? What makes a good material in your?
So that is really a difficult question to answer. So in my group, we don't synthesize the materials ourselves. We have collaborators who do that. So part of what makes a material interesting, and I don't want this comment to be misinterpreted, but it's that other people find it interesting, other people in our research community. So that is not to say that I am all in favor of following the pack. However, the reality of materials physics research is that every research group, they have sort of a niche that they specialize in, an experimental technique or a theoretical technique, which can be applied to different materials in a very, very broad space, the entire periodic table and all its combinations. So to whittle down that big space, and to really make meaningful progress, typically you need a community of people working on similar problems. So that's part of it. So that community of people that sort of make progress in a small niche of a big problem. So that's part of what makes a material interesting. Other things that make a material interesting is that it exemplifies some phenomenon better than other materials in the same category. So for materials in a given category, and when I say category, I can mean like it exhibits the same phenomena like magnetism, or maybe it has similar chemistry building blocks like copper oxygen planes. So however you define a category, some materials sort of are better than others. So sometimes a material that exemplifies the phenomenon you want better than others in its category is the one that you would choose. Sometimes it's the material that works best for the types of experiments you do that determines the decision. So there's not one set of criteria. There's not like a rigid set of criteria, and I think that's okay because if you stumble into an interesting material or an interesting materials class, there's just more and more to do there. As you study more, you discover more complexity or more things that people thought were understood but are not understood, and it just goes from there.
And there's something really, really interesting in there that you mentioned about this relational aspect of making something useful. And I think a lot of people, you'll encounter people who have some big idea and they'll be like, nobody cares about my idea. Why does anybody care about my idea? And I think it's because this often gets overlooked in the scientific education pipeline, that a huge part of doing science is making it relevant to your peers and actually helping them solve problems too. It's really a community effort in a way that gets overlooked, because you look at these giants like Einstein, and sometimes the story behind the scenes of Einstein is lost. His buddy who gave him all the wonderful math and just all of the letters and dialogue. It's sort of overlooked that a huge part of your job as a scientist is to look into the issues and help your colleagues solve theirs. And by doing that, you make yourself relevant, because now your discovery has some actual functional utility in that sphere.
Yeah, absolutely. So science, it's a human endeavor, it's a social endeavor. So even if you are on a single author paper, which is very rare for experimentalists, but even in that case, your science is being done in the context of other scientists that you hope to interact with and impact with. Although I will say that another place to look for a good material to study is precisely that counterpoint that you mentioned. So that space, like, oh, no one's interested in this. So sometimes if you find something that no one is interested in and you can make people interested in it, then that's another way to go about. So there's definitely a place for sort of going against the pack and looking at things that other people are not looking at. But ultimately, science moves forward with more people involved, more people looking at similar problems. So it is important to ultimately come back to the connection.
How do you make space for your students to have that sort of off the path play time, like to try to find things, or in your own work? How do you find space for those things that are sort of high risk, potentially high reward, but you also have to, plug in pieces of the puzzle in order to, stay functionally relevant in the field?
Yeah. I mean, this is something that is important, and it ends up working out in a different way for different students. So students have the constraint that they don't want to be in the PhD program indefinitely, and they're not allowed to be in the PhD program indefinitely, at least at my university. So they need to graduate at some point, and there are milestones that need to be met for that to happen. But within that constraint, there is a lot of room for creativity. I think at the base level, the fact that we're studying complex systems really allows one to be surprised. And I would add to that, the fact that we're studying complex systems using very powerful experimental technology that is widely applicable to a variety of things that happen in materials allows for these surprises to happen. So sort of clarifying what I mean by complexity, we have these materials that have many electrons, and oftentimes we study materials where the interactions between every electron and every other electron cannot be ignored. So we might be starting off with some predictions from our theory colleagues about how the material should behave, and maybe some hypotheses from our end, but nature gives us surprises, and one needs to be open to accepting those surprises, or but doing that in a context of, being critical of all new results you get, and kind of having some foundation of physical principles that you use to explain the results. So yeah, one avenue for exploration is just sort of the surprises that nature gives us by combining elements of the periodic table in different ways and different types of crystals. And then I guess more sociologically, different students have their different talents, and in the long run, my research ends up embracing all of their different talents. So maybe one student is very, very careful, which can make them move slower, but can make them be very rigorous and well suited for kind of understanding and uncovering very subtle things. Maybe another student has a very strong computational background, and they can apply new computational tools, machine learning, to the same type of data we've always had. Maybe another student, they have a background doing a different type of experimental technique, and they can sort of apply the intuition and visualizations that they sort of have very deeply from that background into their new research. So so that's kind of the last avenue of exploration, sort of using people's unique talents and background.
I want to know more about the specific
Yeah. So I sort of wandered off on a tangent there, but the technique that we use it's based on the photoelectric effect, and when electrons fly off after being ejected, they carry information about how they were moving back inside the solid. So the primary technique we use is something called angle resolved photoemission spectroscopy. So the last part of it, the photoemission spectroscopy, that's just photoelectric effect. The angle resolved part means we measure the direction that the electrons fly off. And that direction is related by very simple formulas to the momentum that they had back inside the material. So it's a fairly complex experiment, but to zeroth order, inside a crystalline solid, electrons obey certain energy versus momentum or dispersion relations, and those tell us very detailed information, ranging from how many charge carriers there are, to what is the group velocity of these charge carriers, to what is the effective mass of these charge carriers, and all of these different components that play into sort of how the material responds in simpler situations and more complicated situations. So it can tell us how it would respond to a current or a voltage, if that's the information we wanted to extract, or it can tell us its susceptibility of that material to become something different, to become a magnet, to become a superconductor. So, so these energy versus momentum relations really underlie everything that a material can do and everything that it can become. So it's a very, I would say, general technique that's applicable to every crystalline solid. I really enjoy kind of having the flexibility to, move into different types of materials phenomena with this common tool of being able to understand how electrons move around in a material.
It almost sounds like analogous to these particle colliders. Like you see these trajectories that are coming off of them or something like that, but also somehow like combined with like a cathode ray tube or something where you're having these electrons flying off. Or
I guess the relationship to cathode ray tube is our detector. It's not a cathode ray tube, but it's kind of a modern equivalent of that. Let's say it uses semiconductors to accomplish similar things. As for the analogy to particle physics, it's interesting. So I would say that the actual experiment of smashing things together, that's not really what we do. But there are really deep connections between materials physics and particle physics. So it turns out that many of the interesting phenomena in materials, they can be described, at least at some limited energy range, in terms of language that is used in particle physics. So in particle physics, there's different types of particles, and in the materials physics context, we have things called quasi-particles, which are sort of particles that only exist inside that material. So these quasi-particles, they have names that typically end in "on," but not always. So like electron is one. We don't exactly have a positron, but we have something equivalent. So sometimes electrons can behave like they have positive charge inside a crystalline solid. We don't call those positrons, we call them holes. But mathematically, it's the same as a positron. We have something not related to electrons, but we have phonons. So quanta of sound. And these are particles of atomic vibration, which can sometimes interact with electrons. We also have other types of scenarios that are analogous to things that happen in free space. So sometimes we have electrons in some materials that behave like light. So that does not mean that they move at the speed of light, but that means that they share the dispersion relation of light, namely that the energy is proportional to the momentum rather than proportional to momentum squared. So there are materials that do that, their electrons do that, and there are kind of the opposite scenario where electrons in a material behave like they're very, very heavy, sort of like a muon, I think, or other heavy charged particles. And there are also examples of particles that have not been realized in free space, but can be engineered inside materials. So an example that I do not work on is a magnetic monopole. So those can kind of be engineered in various types of magnetic structures. And one that I do work on to some degree is something called Weil fermions, which in the materials physics context is called a Weil semimetal, and they have sort of electrons that move around in a very specific way that mathematically looks like something in previously a long time ago predicted in particle physics. So I would say that's kind of the deep connection to particle physics. You could even group it together and call the field particles and quasi-particles.
Yeah, I guess I was more just thinking like in terms of these trajectories. You were talking about the information you can learn about something flying off, in this case electrons, how that reconstruction allows you to have some information about the pre-existing state.
I would say in my case, it's, or in the experiments I do, it's a lot simpler. So it's an electron that was inside the material. That same electron flies off at a certain angle and is detected. And that angle where it flies off tells you how the momentum it had inside.
You mentioned phonons too, which are really interesting to me. It almost seems like when we start talking about the wave nature of electrons in a material, and I've seen some pop sci articles trying to tie these two phenomena together. These pressure wave. I don't know how you want to define phonons, but it almost seems like there's some analogous process happening with these.
Good. So let me just clarify. So a phonon is not directly related to electrons. So a phonon is basically a quantum of atomic vibration. And so the closest analogy that, or I wouldn't say, when I say analogy, I mean like a deep physics math analogy that is correct up to a known point. The closest analogy to a phonon is actually a photon, a quantum of light. So these are similar particles in the sense that they are both bosons, meaning you can have many of them in the same quantum state. And thermally, they have some similar behaviors. So the differences between photons and phonons comes essentially from, again, their dispersion relation. So a dispersion relation is just a relationship between energy and momentum that is applicable in a lot of contexts, quantum and classical. So for a photon, the energy is always linear with momentum. For phonons, there are some types of phonons where the energy is also linear with momentum. These are called acoustic phonons, and all of these words and prefixes relating to sound are kind of accurate, because for acoustic phonons, it moves through a solid, sort of like a pressure wave, same as like a sound wave in the air. So there's other types of phonons called optical phonons, which have a different dispersion relation, and to zeroth order, optical phonons just have the same energy no matter what their momentum is. So phonons, these quanta of sound, they're very important to materials, particularly at elevated temperatures. By elevated, I mean non-zero. So most of the thermal behavior of materials is determined by these quanta of atomic vibration. And these quanta of atomic vibration interact with electrons in various ways. And I can measure some of these interactions.
Yeah, well, the way that my mind thinks about this, like you mentioned, phonons are an atomic behavior, but it's difficult for me because electrons are part of the atomic structure at the same time. And so there must be some overlap when we talk about the motion of the atom. We must, in some sense, be talking about the motion of the electron too, in so much as it's part of the atom, right?
Well, yes and no. So I guess So the way that you come up with this notion of atomic vibrations goes back to this this model of like balls on springs, which is a pretty reasonable model, because each atom is kind of at its energy minimum and making small fluctuations around that energy minimum. So the potential energy landscape that each atom finds itself in is ultimately set by all the electrons. However, it's possible to kind of abstract away the presence of electrons and just talk about these atomic vibrations separately. And whatever the electrons are doing is basically captured in the effective spring constant of this imaginary but physically motivated spring. So, so a common way to sort of teach about these quanta of atomic vibration is to do so completely omitting electrons. So basically just the atoms, they have some effective environment, which is ultimately set by electrons, but we don't worry about electrons for now. And you can get, you know, a reasonable way forward there without having to really think about the electrons. But ultimately, you're right. If you want to really calculate very precisely, like what is the speed of sound in this material, kind of on first principles, you need some idea, some information about what the electrons are doing.
Is there anybody working to bridge the gap between those
Oh yeah, no, I mean it's not necessarily a gap. It's just like it's possible to explain quite a lot by keeping the electrons abstract. To really accurately explain behaviors of materials in the sense of how atoms vibrate in that material, you need to have information about the electrons. So if you're actually calculating things very correctly, then you're thinking about electrons as well as the atoms.
Do the electrons function as the spring material that's between the atoms?
So not literally,
Sure. Yeah.
not really literally,
Mathematically.
but mathematically. So like so it for a spring, you have some spring constant, usually given the letter K, which tells you basically how hard you need to pull it to stretch it apart, for example. And when we're talking about atoms in a material and that mathematical spring, it is set by the behavior by the electrons essentially. But the electrons are not literally just in between; they're everywhere. They're sort of diffused everywhere. So.
Well, it seems like what it's saying is that a given material will have a certain characteristic of this electron soup. Like based off of the crystal lattice, based off of the atoms that are inside of it, these delocalized electrons will behave in a specific way that is the spring constant.
Yeah, exactly. I think that's a good way of thinking about it. In the context of like how atoms vibrate, you can think of like an effective electron soup, which has sort of ingredients of the details of what electrons are doing, but ultimately it just sort of gives you the correct spring constant.
It's so interesting.
Yeah.
You said something earlier about there being some electrons that were heavier, like that had that were harder to move. What do you make of that?
So this is, I guess, something that can happen in materials. It doesn't happen in all materials, but it's just an example of how electrons can behave differently when they are inside a crystalline solid as opposed to outside in free space. So the interactions between the electrons and each other, and also sometimes the lattice, can make the electrons behave as if they were heavier. So this can mean, okay, so the way that I visualize this behavior is in terms of what I measure in my experiments, in terms of the dispersion relations. So like for going back to the analogy of a baseball, you have its kinetic energy equal to p squared, that's the momentum, divided by 2m. So m is the mass. And if you make the mass larger, if you think of a graph of energy on the y-axis, momentum on the x-axis, you sort of have a parabola. And this parabola, if you make the denominator larger, it becomes kind of flatter. It becomes a shallower parabola. So I visualize heavy electrons as like a very shallow parabola as compared to like a deeper parabola with a smaller mass. So yeah, this is an example of how electrons can behave differently in a new environment. The new environment being the crystalline solid, and yeah, there's all of these different levels of things happening in a material that we discussed already. So there's like the atoms that can vibrate in place, but their vibrational characteristics are set by the electrons, and then the electrons themselves, they feel impact, or they feel an effect from the periodic lattice of the atoms, and they also feel an effect from the other electrons, which in turn affects their behavior and then cycles back again into how the atoms vibrate in place. So there's all of these moving parts that sometimes interact in very complex ways, but in other cases, this complexity can sort of be abstracted away, and the parts can be viewed separately.
Yeah, it seems kind of related to like the intensive versus extensive properties of a material. Like you have some inherent quality, but as you start to structure it in different ways, you can affect it in newfound ways.
Yeah. So intensive versus. So I would say that. An intensive property is one that does not depend on how much a material you have, and more often than not, we try to work in terms of, or we try to at least share what we've done in terms of intensive properties. So this is something that that sort of was illustrated well in the LK99 work. So usually, so many measurements that we do, they are extensive. They will depend on how much of a material you have. But then when you share it with the world, you want to sort of normalize out those specimen-specific parameters to get something that someone else in their lab, they would measure a different specimen, different mass, different dimensions, and they would hopefully get the same result. So so like an example of intensive versus extensive in this context is like a resistance is something that is extensive. So like you measure a resistance of 10 ohms or something. However, if you want someone in another lab to reproduce it, you would need to, on the graph, show not resistance, but resistivity, where you sort of multiply and divide by dimensional parameters to make it an intensive quantity that another lab could reproduce.
Nice. Yeah, that's something that often gets confused is these qualities, especially resistance, resistivity, conductance, conductivity. People mix them up quite a bit. But yeah, you mentioned the LK99. I'm curious about your thoughts on that in general, and like when you first found out about it, what were you thinking, or how did it seem to you? Was it promising, or you were like, oh no, this is another media scam?
Yeah, so I guess like at this point that we're having this conversation now, the issue has been settled in a very elegant way that maybe we can come back to. But yeah, when I first saw the report, I was skeptical, as was most professional researchers in this field, for a number of reasons. So the first reason is that we see these so-called unidentified superconducting objects show up in preprints every so often. Every couple of years, there's a new one. So we've sort of been down this path before. We know that we've seen kind of similar things posted but not take off on social media. But on top of that, this material, it didn't exactly quack like a duck. So it wasn't exactly what you would expect a superconductor to do if you looked carefully. So like, for example, a superconductor, the resistivity, resistance, whatever, it doesn't matter the multiplicative factor because it's supposed to be 0. And 0 means 0. 0 means like within the noise floor of your instrument at the very least, or some sufficient value much better than like the best conductors we have. So in this material, when it cooled below the transition, the value of resistivity was actually worse than copper at room temperature. So it was about 10 times worse. So it wasn't a superconductor by the 0 resistance metric, and it wasn't even a very good conductor. It was just like an okay metal, I guess. I don't know. And then on top of another aspect where it didn't quite quack like a duck is the the expulsion of magnetic field. So one of the other defining properties of a superconductor is that it expels its magnetic field. So another way to say this is you apply magnetic field and it magnetizes opposite. So the general phenomenon is called diamagnetism, and in the context of a real confirmed superconductor, it's called the Meissner effect. So this material showed some diamagnetism that was different for different configurations of magnetic field. However, many things are diamagnetic. Humans are diamagnetic. Half the periodic table is diamagnetic. So if you were to take the results literally and say, okay, if this were a superconductor, how good would it be? The amount of diamagnetism that was displayed would give like 1% superconducting volume fraction. The aspect that the public really latched onto, because it's something very accessible, was like how the thing floated on a magnet. And this is something that I guess that I didn't have a lot of intuition for, other than knowing that it's kind of how something floats on a magnet can be complex, can be different depending on the poling of the magnets, the shape of the specimen, and other factors. So like floating is not a normal, like if someone discovers a new superconductor, they're not going to post videos and pictures of it floating typically, because most superconductors have transition temperatures that are lower, and you can't really even do that demo. So so that part of it, I didn't really think of it. So anyway, and I would speak for a lot of the research community when I say that. I was like cautiously curious because it didn't seem like the data was really fabricated or anything. There weren't any irregularities. It was presented in a way that, you know, was maybe a little bit, I don't want to use words with negative connotations, but a little bit less professional, a little bit less polished, but that's okay. So like correct data should stand on its own, even if, you know, it's not presented in the most polished way. So I was fine with that. And I was kind of cautiously curious how things would turn out. Not really cautiously optimistic. That's a different thing. I really did not think it was a superconductor because it didn't quack like a duck. I did think that it could be like an insulator to metal transition, as did others who independently came to that hypothesis.
Do you think it's going to find a place in technology still? Is it still an exciting breakthrough, or is it, now that it's not a superconductor, forget about it kind of thing?
So maybe I can say like how the story ended up ending. Yeah. So yeah, all of us, I think all of us watching this take place, who had seen a similar rodeo before, had kind of thought that it would kind of just fizzle away. So people would synthesize, you know, things that were trying to be similar, and, you know, it didn't yield the same results, but oh, maybe the technique, the procedure hadn't been refined exactly the same way, blah, blah, blah. So I figured that it would be like a long slog, and it would be forgotten about before it was disproved. But there was a smoking gun that was found and posted on archive. And that smoking gun was right in front of everyone's noses to begin with. So the original reports of the room temperature superconductor, they posted various measurements, but one of the measurements they posted was X-ray diffraction, which tells you about the structure, how the atoms are arranged in space in this crystal. And in this graph, they acknowledged a known impurity phase, copper to sulfur. And, you know, people, professional researchers and amateurs alike, they got to work trying to follow the synthesis procedure and synthesize some copper-doped lead apatite. But the answer was right in front of everyone's noses, and no one thought to Google that impurity phase that was acknowledged in the original paper, copper 2 sulfide. So copper 2 sulfur, it has a well-known structural phase transition at 380 Kelvin, which is accompanied by a big change in resistivity. So eventually, someone thought to just look at this impurity phase, and that was the smoking gun paper. So they looked at just copper 2 sulfide, and they saw that it had a sharp transition right at the correct temperature. And what they did differently is that they swept the temperature down, and then they swept it back up. And they saw that there was something called hysteresis. So the onset temperature going up was different from the onset temperature going down. So this is very common for a structural phase transition in a crystal. So a structural phase transition is where the atoms are arranged in one specific order in space, and then the same atoms at a certain temperature, they sort of go into a different structure. So for example, you can have like a cubic arrangement transforming into like a rectangular prism type of thing, an elongated cube. I don't have the right words, but yeah, so this hysteresis is characteristic of structural phase transitions, but not superconductors. So in a superconductor, you never see hysteresis. You always get the same temperature going up and coming back down. So that was sort of a smoking gun experiment that this was not a superconductor, and that the resistivity signal that was reported was just from this impurity phase. So this is a really good example of like how in hindsight, good science is 2020. So in hindsight, this impurity phase causing the entire signal is so obvious. So as for like, is copper 2 sulfide useful? I think it's an active area of research. So if you search Google Scholar, copper 2 sulfide, you'll get lots and lots and lots of scholarly works, dating back decades. It's an interesting material. It's a thermoelectric material, so it can turn heat into electricity or vice versa. It has also been explored in the context of solar photovoltaics. So I don't know how interesting it is in the spectrum of other materials explored in those applications, but it's an active area of research in its own right.
Do you have any more LK99 questions? So I want to change topics otherwise.
No, I think that was a really good explanation. I like you said, it's easy to see in retrospect, to go back now and to piece it together. At the time, I was like everyone else, kind of swept away by it, just because it was the first time that I'd really seen a scientific idea go viral on Twitter or really anywhere.
Or a scientific idea in materials physics. I would say that was the first time I've seen something like that in my professional career.
And it was just kind of cool to watch because it became suddenly this very democratic affair where people were trying to reproduce it in their own houses, and all these teams got together and they were working it out. And for a very brief moment, I saw the spark of how I wish science went more frequently, where somebody comes up with something and instead of it just being relegated to the scientific journals, it sparks something inside of people who then want to pursue it. And so I don't know. I think that maybe it was that chemistry kit from everybody's childhood coming back for a second, where they remembered what it was like to blend stuff together that the instruction manual didn't tell you about.
Yeah, I love that aspect of it as well. There's sort of this perception that scientists in academia, they want to gatekeep, and I can't speak for everyone else, but for me, it's certainly quite the opposite. So I'm a researcher, but I'm also an educator. So I teach students who don't pursue this professionally, but I still it's my job to teach them, and I hope to spark an interest in them. So like I was really happy about all of those things that you mentioned.
So at the beginning, you mentioned that you are actually inside of an astronomy department, essentially.
Physics and astronomy.
Physics and astronomy. Do you have much crosstalk with the astronomers? Because we have just cracked open, we have a few conversations coming up with some really interesting astronomers that are looking at the presence of magnetic fields in galactic evolution. And, just in our pre-show meeting, we're kind of talking about how does this happen, and it's essentially an electronically induced magnetic field. And so, electron motion, conductivity, resistivity, these things seem like they are in the frontier of understanding how stars evolve, how galaxies evolve. Do you have any conversations going with those people, or are you guys kind of on opposite ends of the building?
I guess not necessarily like professional conversations, research related in very technical ways at this point. But never say never. It's there's a reason that all of these seemingly different disciplines are kind of housed in the same department. So people that study materials here on Earth, people that study the early universe via the cosmic microwave background, people that smash particles into one another, and so on and so forth. So these are on the surface very similar things, but they all use these different subfields of physics. They use very similar tools. They all combine all of these disciplines that we learn in the undergrad education. They combine them in different ways to kind of be applicable to these very different regimes of nature. So I don't at this time have collaborations with astrophysicists and cosmologists, but never say never, I guess.
Well, I think it's a very, very new field in some sense. This, the gentleman that we talked to, and I can't remember his name right now, but he was saying that there's basically 3 galaxies that have been really examined in terms of their magnetic structure. And this just seems like it's going to open up the door to material sciences, in particular conduction, and how these systems are interacting with one another. And so I don't imagine that it's necessarily something that you might have encountered too much so far, but I think it might be something in the future.
Yeah, maybe so.
But I don't know. This is you've given us a ton to think about here, and I feel like I have a little better understanding about the material nature of these conductors. I need to go back and think about it and try to bring some of these into our future discussions.
Yeah, I hope that we have the chance to talk to you again, because there's a lot of stuff about the harmonic nature of all of this that we've kind of started to explore, but it's very difficult to talk about because it's easiest for me to talk to someone when I can come up with a visual model, because then I feel like I can convey that to somebody who's listening who doesn't have one yet. Because I'm like, this is the picture that I see in my head, and if this is the picture, then I can check with you to make sure that it's the right one and then pass it on to somebody else. But with the complex harmonics that are happening inside of materials, I don't have that intuitively for myself yet. But it seems like that's kind of at the heart of what you're characterizing, because you're taking this relationship between the atoms and their electrons to say something about the material. And so there's this, we've gone very deep in context of the specific aspects of the atoms and the electrons, but hopefully we can have another conversation down the line about the bigger picture and how it all fits together, because you have a really insightful perspective on all of this that I really appreciate.
Yeah.
And if people want to find out more about your work, where's the best place to do that? Do you have a lab website, or do you do Twitter or anything like that?
I found you on Twitter.
Yeah, I have a lab. So if you Google my name, you'll get my lab website, you'll get my Twitter. I was really active on Quora back in the day as well. So I sort of explain concepts related to materials physics, superconductivity there.
Nice.
Very cool.
Well, yeah, thank you for your time. I really appreciated, picking your brain a little bit, and I wish you all the best of luck in coming up with the next generation of civilization.
Thank you. We'll see about that. It's been fun.
All right. Have a great rest of your day. Thank you so much.
You too.
All right.
Bye.
Bye, everybody.
Bye.